welcome to the third lesson on the module second, which is on analysis of strain. This particular lesson we have designated as analysis of strain 3. In the last lesson we have discussed certain aspects of strain. In this particular lesson we will be discussing some more aspects of strain. Well, it is expected that after this particular lesson is completed, one will be able to understand the concept of normal strain in a 3-dimensional stressed body, and thereby we can go for the generalization of Hooke's law. One should be able to understand the concept of determinate and indeterminate systems. Also, one should be able to understand the concept of compatibility, which will eventually arise out of this indeterminate system, which we are going to discuss subsequently. Well, this particular lesson includes the recapitulation of previous lesson, which we will be doing that through the questions which we have posed last time. We will be discussing those questions, and eventually it will give you the recapitulation of the previous lesson. The evaluation of axial strain in a 3-dimensional stressed body, the concept of determinate and indeterminate systems, and thereby the compatibility criteria, how it will arise out from that particular system, that we will look into, and finally the evaluation of forces for indeterminate systems. Well, before we proceed with this particular lesson, let us look into the answers of the questions which we had posed last time. The first question which was posed was the what is Poissons ratio and what is the range of its values. Now, if we remember that last time we had discussed that if a body which is subjected to an axial pull is held up at this end and is being pulled by axial load P, eventually this bar extends or elongates, and this elongation we had indicated by delta, and thereby there is contraction on the other sides. Now, the French scientist Poisson demonstrated that the ratio of this strain, which is the transverse strain, to the axial strain is constant for stresses within the proportional limit, and this particular constant is designated as Poissons ratio. So far as the definition of the Poissons ratio is concerned, it is the ratio of the lateral strain to the longitudinal strain. And if you remember, we had designated this mu as minus the transverse strain to the longitudinal strain. And remember that we had put this particular sign as negative, because when this is being pulled by an axially tensile pull, then there is contraction on other sides, and this negative sign indicates that there is contraction. Similarly, if this particular bar is subjected to an axial compressive force, where the length in the axial direction is going to shorten, thereby the other two directions it is going to increase, and eventually that shortening of the axial length is being designated as negative to the expansion of the other two sides, and that is why this negative sign comes in. Well, also we have said that what is the range of its values. Now, Poissons ratio for different material varies, but over a very small range of values. Generally the values vary between 0.25 to 0.35. For some limiting materials we get values in the range of around 0.1, or for some material we get in the range of 0.5, which is that of rubber, and in fact 0.5 is the limiting value on the other side. So, in the sense that the range of the values in general we can say between 0.1 to 0.5, and most of the material lies between 0.25 to 0.35. 0.5 is the maximum value of the Poissons ratio. Well, the next question posed was, what is shear modulus and what is its unit? I am sure this particular question you all are aware of. Well, let me just discuss briefly. We had said that shear strain in an elastic body is proportional to the applied shear stress. Now, this is a body which is acted on by this is subjected to the surface force, and thereby the shear stress tau is equals to the applied load divided by the cross sectional area will give us the shear stress, and within proportional limit, within the limit of the proportionality, the shearing strain is proportional to the shearing strain which we have designated as gamma. So, tau is proportional to gamma, and removing this proportionality sign, we say tau is equals to G times gamma, where G is termed as shear modulus. This is called as shear modulus. And this has the unit, this is similar to the unit of modulus of elasticity, which is in Pascal or in Newton per meter square, or megapascal MPa, which is 10 to the power 6 times Newton per meter square, or gigapascal. So, that is the unit of the shear modulus G. Well, the third question is, how will you evaluate strain in a 3-dimensional stressed body? Well, let us look into the body which is subjected to, let us assume that these are the 3 directions, this is x, this is y, and this is z, and correspondingly as we have defined earlier, the stress components are sigma x, sigma y, and sigma z. Now, as we have seen earlier that when a bar is subjected to axial pull, the stress at any cross section is P divided by A, the cross sectional area, which we have designated as normal stress sigma x, and correspondingly the strain in the axial direction is epsilon x, and as per Hooke's law, the epsilon x is equals to sigma x by E. Also, we have noted from the concept of Poissons ratio that if we have axial load acting in the x direction only, and thereby there is strain in the x direction as epsilon x, the strain in the other 2 directions y and z direction, epsilon y is equals to epsilon z is equals to minus mu times epsilon x. This is the as per the definition of Poissons ratio. Also, if we consider that the body is subjected to the axial load in the y direction instead of in the x direction, that means we have a bar which is subjected to load in the y direction, which is P. Thereby, the stress again at any cross section is P by A, and let us call that stress as sigma y, since the P is acting in the y direction. So, this is P by A, let us call this as P suffix y, this is P suffix x. Now, also because of this application of the load, there is strain in the y direction, which we designate as epsilon y, and that is going to be equals to according to the Hooke's law is sigma y by E. Now, due to Poisson's effect, then the strain in the x and z direction will be epsilon x is equals to epsilon z is equals to minus mu epsilon y. And if we substitute the values of epsilon x and epsilon y in these corresponding places, this is minus mu sigma x by E and this is minus mu sigma y by E. Likewise, if we assume that the body is acted on by force in the z direction by P, then the stress at any cross section, let us call that as sigma z, is equals to again P suffix z by A. Also, the strain corresponding to that in the z direction is epsilon z, which is equals to sigma z by E. Epsilon z is going to be equals to sigma z by E. As we have seen in the previous cases, that when it is acted on by the load P either in the x direction or in the y direction, we could compute the strains in the other two directions. In the present case also, when it is subjected to axial pull in the z direction and is the strain which is acting in the z direction is epsilon z, the corresponding strain in the epsilon in the x and y directions are epsilon x and epsilon y, which is equals to minus mu times epsilon z. So, in this particular case, epsilon x is equals to epsilon y is equals to minus mu times epsilon z, which is mu times sigma z by E. Hence, if we combine all three cases together, if we superpose them, since we are considering the body within the elastic limit, hence the superposition is valid, we can combine them together with the individual results. If we join them together, we will get the same effect when all three are acting simultaneously. So, in that particular case, when all three are acting, we can write then the strain in the x direction epsilon x is equals to the sigma x by E because of the load which is acting directly that, and the strain which we are getting in the x direction because of y and z direction is equals to mu times sigma y by E minus mu sigma z by E, or this is equals to sigma x by E minus mu sigma y plus sigma z by E. Likewise, the strain in the y direction epsilon y can be written as sigma y by E minus mu times sigma x plus sigma z by E. And epsilon z is equals to sigma z by E minus mu times sigma x plus sigma y by E. Now, if we reduce this three dimensional form to a two dimensional one, keeping the x and y plane, then the stresses which will be acting are sigma x and sigma y, and eventually sigma z is equals to 0. In that particular case, we will get epsilon x as equals to sigma x by E minus mu sigma y by E, and epsilon y is equals to sigma y by E minus mu sigma x by E. These results we have seen it earlier. So, this is in fact in a generalized form of Hooke's law, which is applicable in case of a three dimensional body. So, in three direction epsilon x, epsilon y, epsilon z, the strain in the three direction can be represented in terms of the stresses sigma x, sigma y and sigma z, and in terms of the modulus of elasticity E. Well, these are the aspects we have discussed. Now, let us look into the important aspects which we do come across in many problems related to different fields, which we designate as a statically indeterminate problem. Now, when we talk about statically indeterminate problem, naturally we will have to first know what we really mean by a determinate system. We have seen earlier that we have three sets of equilibrium equations in statics. There is summation of horizontal forces as 0, summation of vertical forces as 0, summation of moments as 0. These are the equations of equilibrium. Now, if we consider any system from which we can evaluate the reactive forces by using these equilibrium equations, we call those systems as statically determinate. You see, if equilibrium equations are adequate, this is important, that equilibrium equations are adequate to evaluate the reactive forces, then the system is called as determinate. Let us look into some example. Last time we did a problem, say we have a rigid bar which is pinned at this particular end and is held up by a rod and is subjected to a vertical load P. Now, if we draw the free body diagram of this particular configuration, removing these supports, the free body diagram will look like this. This bar being pin connected is subjected to axial loads only. Hence, there is a axial pull PB, and these are the reactive forces R and H, and this is the external load P. This is the free body diagram of this particular system. Now, in this particular free body diagram, the unknown forces are, the reactive forces are H and the axial pull in the member PB. So, these three parameters can be evaluated from the equations of static. That means, if we take summation of horizontal forces equals to 0, summation of vertical force equals to 0, summation of moment equals to 0, and if we apply these three equations for this, we can evaluate R, H and P readily from these equations. Hence, this particular system is statically determinate. Now, let us change the configurations of this particular system a little, and instead of supporting this rigid bar with one wire alone, this is connected by two wires of this particular form. Now, these rods will undergo extension because they are subjected to axial pull when this particular load will be acting. Now, if we try to plot the free body diagram of this particular system, this is the rigid bar which is pinned over here. Now, this is subjected to the reactive force, vertical and horizontal as before. Here we have the applied load P. Now, two rods which are supporting this bar will have axial pull in the rods. So, there are forces which are reactive forces R, H, and let us call this as P1 and P2, which are under the action of the axial load P or the transverse load P. Now, in this particular case, if you look into, we have 4 unknown reactive unknown forces R, H, P1 and P2, and since we have only 3 equations of statics, so this particular system cannot be solved using these equations of equilibrium alone. Hence, there are systems like this where you cannot solve or evaluate the forces, unknown forces, based on the equations of equilibrium alone or equations of statics alone. Now, you need an additional equation here over and above these 3 equations to solve this unknown reactive forces. So, this is what is indicated here. If the number of unknown forces, in a system exceeds the number of equilibrium equations, then the system is called statically indeterminate system. So, the system is indeterminate because we cannot solve the unknown forces using the equations of equilibrium, but then that does not mean that we cannot evaluate the unknown forces for those indeterminate systems. So, for the solution of these indeterminate systems, we will have to find out ways by which we can generate additional equations from which we can solve these particular unknown reactive forces. So, the indeterminate problems are the one in which a statically indeterminate problem always has geometric restrictions imposed on its deformation. In fact, from this the compatibility criteria comes in. The indeterminate system always gives rise to geometric restrictions, and these geometric restrictions, when they are expressed mathematically, this gives rise to the equation of compatibility. So, we have seen that we have 3 equations of equilibrium, which are statical equations of equilibrium. Over and above, if we write down the equations of compatibility which do arise from these geometric restrictions for the deformation, this equation of compatibility along with the equations of equilibrium will lead us to the system of equations from which you can solve the unknown reactive forces in the indeterminate system. So, now you can distinguish between a determinate system and indeterminate system. Once again, a determinate system is the one for which the unknown reactive forces can be evaluated based on the equations of equilibrium, and for indeterminate systems we cannot evaluate the unknown reactive forces based on the equations of equilibrium alone, and for that we need to have additional equations depending on the number of unknown reactive forces you have, and those additional equations do generate from the equations of compatibility, and the equations of compatibility is nothing but can be written down in terms of the geometrical constraints or the restrictions which we impose in terms of the deformation. So, compatibility conditions provide additional equations for evaluating unknown forces, and thereafter we can adopt this Hooke's law to express the deformation in terms of forces, because we first write down the compatibility criteria based on the deformation, and then we adopt Hooke's law to relate the deformation to the forces, and finally we get equations from this compatibility criteria which help us to solve the unknown reactive forces. Well, after looking into the aspects of this indeterminate system, now we are ready to look into the problems where such indeterminacy comes in. But before we proceed with those indeterminate problems, let us look into the example problem which we discussed or which I gave it to you last time for the solution. I hope you could do it, but let me just explain to you so that you can check your solution with this. Now, the problem which was posed to you last time is that determine the elongation of the tapered cylindrical aluminum bar caused by 30 kilonewton axial load, and the value of E is given over here. And in this particular problem, it is given that the diameter of this bar at this place is 20 millimeter and the diameter at this end is 30 millimeter, and over the length of 400 millimeter it is varying gradually. Now, our job is to find out the deformation, to find out the elongation of the gradually varying member. And if you remember, we had discussed that how do we compute the elongation in such members, since the cross section is varying at every position, hence the cross sectional area is not constant, and we cannot compute directly delta from the expression P L by A E, where A is no longer a constant parameter over the length L. Hence, what we need to do is that we got to compute delta as equals to integral over the length of the member as P dx over the small segment, we say the area which we write as a function of x times E, and from this expression we compute the value of delta. Now, if we take a section which is at a distance of x from the left end, then the diameter at this particular section D is equals to, this is 20 plus this is 30. So, 30 minus 20 is the value at the end. So, at this particular point it will be the ratio of x to 400. So, this is 30 minus 20 times x by 40, and 30 minus 20 divided by 2, and twice of that, since on this side we have extra, on this side we have extra over 20. So, this is 2. So, 20 plus 30 minus 20 times x by 400. So, this is nothing but equals to 20 plus x by 40. So, this is the diameter at this cross section which is at a distance of x from the left end. So, let us compute now that what is going to be delta for this particular case. So, we have the bar which is tapered, and we have just seen that at a cross section which is at a distance of x, the diameter here D is equals to 20 plus x by 40 millimeter. Hence, the cross sectional area A is equals to pi by 4 times 20 plus x by 40 square, and delta is equals to integral 0 to 400. The load is 30 kilonewton. So, 30 times 10 to the power 3, so much of Newton dx L by A, which is pi 20 plus x by 40 square times 4, pi d square by 4 times E, which is 72 GPa. So, 72 times 10 to the power 9. So, so much of millimeter, and this if we compute, this will give rise to, this is equals to 120 divided by 72 pi into 10 to the power minus 6, integral 0 to 400, this is dx by 20 plus x by 40 square. Now, if we substitute 20 plus x by 40 as say z, we get dz as 1 by 40 dx, and when x is 0, z is 20, and when x is 400, z is 30. So, it varies from 0 to 20 to 30. So, this integral gets transformed to this particular part as integral 20 to 30 dz 40 times dz divided by z square. So, this is nothing but minus 1 by z integral, which is 20 to 30. Eventually, then this comes as, this is equals to, so delta is equals to, if we compute the whole thing, it is 4800 into 10 to the power minus 6 divided by 72 pi into 1 by 20 minus 1 by 30, and this is equals to 3.53 into 10 to the power minus 7. So, this is the value of the delta which we get from the. So, this is the computation for the value of the delta for the varying diameter. So, for a member which is tapered, the member which is tapered, and if we know the diameter set is 2 n's, we can compute that how much is the elongation that the member will be undergoing. Hope you could compute this. Well, let us look into the next problem, next example, which is in terms of the indeterminate problem. Now, here a bearing plate connected with a copper rod is placed inside an aluminum sleeve as shown in figure. So, here this is the bearing plate, this is the bearing plate, and this bearing plate is connected with the copper rod going inside. So, this is the copper rod and this is the aluminum sleeve, is placed inside an aluminum sleeve as shown in figure. The copper rod is 0.05 millimeter longer than the sleeve. So, this gap is 0.05 millimeter. So, the copper rod is longer than the sleeve by 0.05 millimeter. Now, we will have to find the maximum safe load that can be applied to the bearing plate. On this plate, the maximum load P that can be applied, that has to be computed. The cross sectional areas of copper rod and aluminum sleeve are 1000 millimeter square and 2000 millimeter square. E values of copper and aluminum are 1.4 into 10 to the power 5 MPa and 0.7 into 10 to the power 5 MPa. Allowable stress in copper is 100 MPa and that in aluminum is 50 MPa. So, the maximum permissible stress in aluminum and copper are given. The cross sectional area for the copper and the sleeve, aluminum sleeve, are given. Now, our job is to compute that what will be the value of P which can be safely transferred onto top of this bearing plate. Now, let us look into the free body diagram of this particular system. If we cut off the sleeve at some distance from the top, then this is the bearing plate, the copper rod is attached with this, and this is acted on by load P. Now, when the rod will get compressed, and cover up the distance 0.05 millimeter, eventually it will touch the slip. So, this bearing plate along with the copper rod, it has compressed, covered up that 0.05 millimeter gap between the slip and the copper rod. That much of compression has, or the deformation has undergone into the copper plate, and eventually the bearing plate is going to touch on the slip, and when the bearing plate will be touching the slip, then the load which is acting on the bearing plate will be transmitted to the slip. So, at this free body diagram, if we now transfer the reactive forces, those are acting on this, they are the force in this copper rod and the forces in a combined form in the slip, these two together. Let us call that the load in the aluminum. So, we have these two forces P C and P aluminum, which are being generated because of the externally applied load P. So, if we write down the equilibrium equation, so equilibrium of this particular system is that P is equals to P C plus P aluminum. This is equation 1. Now, in this particular system, we cannot have any other equilibrium equation. So, we have only one equation of equilibrium, and there are two unknown forces, and they are P suffix C and P suffix Al. So, two unknown forces and one single equation, hence we cannot solve this particular system unless we have an additional equation, and this additional equation can be generated from the compatibility criteria in terms of the deformation, and then we can solve for these two unknown forces. So, now let us look into that what is going to be the compatibility equation in this particular case. Now, let me look into another free body diagram of the top part of the system. So, this is the bearing plate along with the copper rod, and the sleeve is in this location, and this is the gap, since copper rod is 0.05 millimeter greater than the sleeve. So, this is an exaggerated form, and let us say after deformation the bearing comes in this particular position. Hence, the deformation that the copper rod undergoes is this much. This we call as delta C, and in the process when copper rod deforms to this extent, and if this is the position where the bearing plate has come, then the deformation which is existing in the, or which has occurred in the aluminum is this much. This we call as delta aluminum. So, from this particular configuration we can write delta C is equals to delta aluminum plus 0.05 millimeter. So, this is the criteria which is getting developed from the compatibility of the two systems, that initially when the load is applied on this bearing plate, first the bearing plate along with the copper rod has to deform to the extent of 0.05 millimeter, then the load gets transferred onto the slip, and then the slip deforms, and this is the final level of the deformation. And if this total deformation we call as delta C, then delta C consists of two parts. One is this 0.05 millimeter gap which has to be made up by the copper tube or the rod along with the deformation of this slip. So, this is the compatibility equation, and now if we apply Hooke's law to this deformation equation, we can get additional equation from which we can evaluate Pc and P aluminum. Now, delta C we can write in terms of the load and cross sectional area, which is PL by AE. Let us call that PC is the force which is acting in the copper rod times length of the copper tube LC divided by area AC times EC. This is equals to P in the aluminum times L of aluminum by A of aluminum times E of aluminum plus 0.05. Now, in this particular case, since the values of limiting stresses are given, let us compute the values in terms of stresses. Now, as we know, P divided by the cross sectional area is the stress. So, this particular part PC by AC we can write as the sigma C, the normal stress in the copper rod, and PL by AL we can write as sigma aluminum, which is the normal stress in the aluminum sleeve. Hence, this compatibility equation in terms of stresses we can write as sigma C times LC divided by EC. This is equals to sigma aluminum times length of the aluminum divided by E of aluminum plus 0.05. Now, if we substitute the values, the value of LC, the length of the copper tube, the length of the aluminum sleeve is given as 250 millimeter, and since the copper rod is 0.05 millimeter longer than the aluminum sleeve, so the length of the copper rod is 250 plus 0.05, so 250.05. So, sigma C into 250.05 is the length of the copper rod divided by E of copper rod, which is 1.4 into 10 to the power 5. This is equals to sigma aluminum times the length of the aluminum is 250 divided by E, which is 0.7 times 10 to the power 5 plus 0.05. Now, this if we compute, this comes as 0.00179 times sigma C is equals to 0.00357 sigma aluminum plus 0.05, or sigma C is equals to 1.995 times sigma aluminum plus 27.93. Now, this is the relationship between the stress in the copper rod to the stress in the aluminum rod. Now, here the limiting values of the stresses in copper and aluminum is given. Now, the maximum allowable stress in copper rod is 100 MPa, sigma C max is 100 MPa, as sigma aluminum allowable or max as you call it as equals to 50 MPa. Hence, if we take the value of allowable stress in aluminum as 50 MPa and if we substitute it here, then we get the value of sigma C as equals to 1.995 times 50 plus 27.93, and eventually the value of sigma C comes as 127.68. MPa. Now, since the maximum allowable stress in copper is 100 MPa, so we cannot afford to go for stress up to this level. Hence, we cannot apply the stress in the aluminum up to 50 MPa, because if we go up to a stress level of 50 MPa in aluminum, then the stress level that is expected in the copper rod is going beyond the allowable stress of 100 MPa. Hence, we cannot allow the stress in aluminum slip to go up to its limiting value, which is 50 MPa. That means, we will have to limit the stress in the copper rod up to 100 MPa and check that how much stress it can generate in the aluminum slip, from which we can evaluate the safe load. Hence, if we go the other way, limiting the value of sigma c to 100 MPa, let us see how much we can get the value of sigma aluminum. So, we limit the value of sigma c as equals to 100 MPa, and from the relationship which we have, sigma c is equals to 1.995 sigma aluminum plus 27.93. The value of sigma aluminum comes as 100 minus 27.93 divided by 1.995, and this is equals to 36.13 MPa. So, by allowing the copper rod to go up to its limiting value of 100 MPa, the maximum stress that can be generated in the aluminum slip is 36 MPa, which is well within the allowable limit of the 50 MPa stress. Hence, the safe load that can be transferred on the bearing without causing any distress to the member is equals to P C plus P aluminum, safe load in the copper and the aluminum, copper rod and the aluminum slip. This is equals to sigma c into area of the copper rod plus sigma aluminum, which maximum we can allow, multiplied by the area of aluminum. Now, this is equals to 100 multiplied by the cross sectional area of the copper, which is 1000 millimeter square, plus sigma allowable is 36.13 for aluminum multiplied by 2000 millimeter square, and this eventually gives 172.26 kilonewton. So, the load which can be applied on the bearing must be less than or equals to 172.26 kilonewton, and thereby the maximum stress that can be generated in the copper rod is 100 MPa, but the aluminum slip will not go up to 50 MPa, but it will be well within 50 MPa, and thereby the whole system will be safe. Well, let us look into another example of such indeterminate system, which I was citing as an example, that AB is a rigid bar. A rigid bar AB is supported by a pin at B and by two rods. This bar is pinned at B and supported by two rods, which are at a distance of 0.8 meter and 1.8 meter from B. This rod is a steel rod of length 1 meter, and this is aluminum rod of length 2 meter, and this bar is subjected to a load of 100 kilonewton at the point A. Now, we will have to find the stress in each bar or each rod, and the cross sectional area of those bars are given. Steel bar is 500 millimeter square and that of aluminum bar is 300 millimeter square, and the value of E are given as 2 into 10 to the power 5 and 0.7 into 10 to the power 5 MPa for the steel and the aluminum. And let us assume that the weight of this bar is negligible. Now, as we we had seen before, that let us write down the free body of this system and write down the equations of equilibrium and observe what happens. So, if we take the free body, this is the rigid bar spin at this end, acted on by two rods, they are steel and aluminum, and at this end we have the reactive forces for the pin, and at this end the load 50 kilonewton, I am sorry 100 kilonewton is acting. Now, if we like to find out the forces, let us take the moment of, now here we have 1, 2, 3, 4 unknown parameters, and we have 3 equations of equilibrium. Hence, we cannot solve it in a statically determinate form or using the equations of equilibrium. Hence, we will have to have an additional equation which are generating from the equation of compatibility. And the equations of equilibrium, if we take the moment about B, then we have 100, moment about B is equals to 0. So, we have 100 into 2.5, this is equals to Ps into 0.8 plus P aluminum into 1.8. So, the equilibrium equation is 0.8 Ps plus 1.8 P aluminum is equals to 250. So, this is the equations of equilibrium, this is the equilibrium equation. Now, from the compatibility, now if we, since this load is acting at this end and this is the pinned end, this will undergo, the bar will move in this particular form, and this will move in the form of a circle with the center of this particular point. Now, this being a smaller deformation, we consider this arc as a straight length, hence this is a triangular form. So, at these locations this bar will undergo deformation, and let us call this deformation as delta S and the deformation here as delta aluminum. Hence, the compatibility is that delta from this particular triangular configuration we can write delta S by 0.8 is equals to delta aluminum by 1.8. So, this is the compatibility relation, and delta, if we write in terms of P, in terms of using the Hooke's law, which is PL by AE. So, this is PS LS by AS ES, that is for steel, is equals to 0.8 divided by 1.8 times P aluminum length aluminum divided by A aluminum times E aluminum. And if we substitute these values, we get the relationship between the load in PS and the force in P aluminum. Eventually, you will get PS as equals to 4.233 P aluminum. So, this is the second equation. So, now from these two equations 1 and 2, we can solve for PS and P aluminum, and if we substitute these values of PS over here, we get the values of P aluminum as equals to 48.2 kilonewton, and thereby PS is equals to, we get as 204.04 kilonewton. So, these are the forces that is acting in these two rods, and once we know the forces that is acting, then the stresses, the stress in the aluminum bar, stress in aluminum rod, this is equals to P aluminum by A aluminum, which is cross sectional area of aluminum, which is equals to 48.2 is the load, 10 to the power 3, so much of Newton, divided by 300 is the cross sectional area, and this eventually comes as 160.7 MPa. And stress in steel bar or steel rod, this is equals to P steel by area of steel, which is equals to 204.404 into 10 to the power 3, so much of Newton, divided by 500, and this comes as 408.08 MPa. Now, here though the stresses, level of stresses appear to be a little higher, maybe beyond the limiting capacity of this material. However, theoretically we are computing what are the values of the stresses. If the limiting values are given, we can always compare and we can say whether this is safe or unsafe, whether the system will be able to withstand this load or not, that we can always compute. Well, now we have another problem which is similar type, but of little variation, that the rigid bar AB of negligible weight is supported by a pin at B and by two vertical rods of aluminum and steel. You will have to find out the vertical displacement of the 50 kilonewton weight at this location, how much displacement it undergoes, and the parameters of these members are given. So, this problem is assigned to you. Solve this problem. Next time I will give the solution for this. Now, in conclusion, to summarize the whole thing, we can say in this particular lesson we had included the concept of strains in a 3-dimensional stressed body, and concept of determinate and indeterminate systems. We know clearly now what is really meant by determinate system and indeterminate system, and thereby how to arrive at the compatibility criteria to solve for the unknown reactions in indeterminate system, and the examples to demonstrate, to evaluate the forces in indeterminate system. Well, these are the questions posed for you. What is meant by indeterminate system and how is it different from determinate ones? What is meant by compatibility equation, and what will be the effect of temperature variation in a stress system? Look into the answers for this. We are going to discuss this again in the next lesson. Thank you very much. Welcome to the fourth lesson of module 2, which is on analysis of strain, part 4. In the previous lesson we have discussed some aspect of analysis of strain, and in this particular lesson we are going to discuss some more aspects of strain analysis, and let us look into those aspects.